Hi, everybody. This is Tony DeLigio with Plastics Technology Magazine, and I'd like to welcome you to today's webinar, Moldmaking Simplified, How Westminster Tool Applied Metal 3D Printing to Boost Efficiencies. Today's webinar is presented by Mantle, and in it we will discuss how tool shops are using Mantle's hybrid metal 3D printing system to lower lead times and costs by eliminating or reducing toolmaking operations. Specifically, Westminster Tool will explain how they are applying Mantle's technology to boost efficiencies across their organization. We will have two presenters today, Ethan Wright-Toe, Director of Marketing at Mantle, and Hillary Thomas, Strategic Leader at Westminster Tool. Ethan has extensive experience in technical marketing for design and manufacturing. He previously ran the technical marketing team at 3D printing manufacturer Desktop Metal, and before that, he worked on the rapid prototyping team at MIT Lincoln Laboratory. Ethan has a master's degree in engineering from Boston University and a degree in mechanical engineering from the University of Colorado in Boulder. Hillary Thomas, rejoined Westminster Tool, her family's business, after working as an international sales strategist. Her experience in leading and promoting corporate change through training programs has aided Westminster Tool's philosophy of hiring for character and training for skill. Today, her focus lies on business development, diversification of technical capabilities, and leveraging the latest technology in plastics industry for injection molding. So with that, I'll hand it over to Ethan and Hillary.
Awesome. Thank you for that introduction, Tony. As Tony mentioned, my name is Ethan. Today we're going to be talking about Moldmaking Simplified, how Westminster Tool, or Hillary talked about how Westminster Tool has applied metal 3D printing to boost efficiencies. Just a little brief introduction to Mantle. Mantle was founded in 2015 in San Francisco with the goal to solve the real problems of manufacturers and OEM. We did this through developing a metal 3D printing technology that we call TrueShape. We'll talk a lot about the TrueShape technology today, but this technology is solely focused on printing manufacturing tooling. So what sets Mantle apart from a lot of metal 3D printing technologies is that we're very, very focused on solely printing manufacturing tooling, and that we're here to solve the real problems that we see manufacturers and OEMs experiencing, like yourselves, every single day.
Just a little bit about Westminster Tool. We are a predominantly injection mold builder located in the northeast corner of Connecticut. You've probably heard about us. We've gotten a lot of representation on our culture. We have a pretty unique culture here focused on emotional intelligence, accountability, improvement, and learning. We have an average age of about 35, and so we've definitely gotten a lot of attention for that. But we really pride ourselves on being manufacturing solution providers. So we really like to roll up our sleeves and solve problems for our customers. And today we're going to talk to you a little bit about some of the ways that we've done that by partnering with Mantle. Sorry. In terms of what we make at Westminster Tool, on the left, you can see we predominantly build complex injection molds, anywhere up to around 64 cavity, anything up to a 350-ton press so that we can sample it in-house before shipping it. We focus on intricate dimensional challenges where our pre- and post-value add services can be utilized. We also manufacture composite tools and high-performance components for the aerospace industry, things like molding PEEK, Torlon, Ultem, and we're AS9100, ISO 9001 certified, and ITAR registered.
So quick agenda for today. We'll start by talking about 3D printing and its role in toolmaking, both in the past and where it is today. We'll talk about Mantle's technology, how it works. Hillary will talk about Westminster's tool experience with Mantle's technology and how they're utilizing it here in their tool shop. And then look at a bunch of different use cases of Mantle's technology, some different applications of how a lot of different people are using this technology and adding value to their organizations. So quickly, we want to start with just one quick poll here. We'd love to understand who we're talking to today, who's on the line here with us today. We thank you for being with us. So how would you describe your business? Just give people a couple seconds here to answer. It gives us a good understanding of who we got on the line here today. Awesome. So it looks like we have a pretty diverse crowd here, which is always good across really all of these, which is always good to see. All right, awesome. Thanks for giving us a better understanding.
So just wanted to kind of talk about and kind of reiterate, get us all on the same page. Based on the poll here, it definitely looks like we're a diverse group today. But I wanted to talk about the specific needs of the tooling industry, in particular, how it relates to 3D printing. So tooling steel is not a one size fits all, and it's not an applicable steel to everything else. We need we need our components to be very high accuracy. At Westminster Tool, we're splitting tenths, so we need something that can get right down into those tight tolerances that we need in order to deliver really good quality parts shot after shot. We need steel that's durable. We need it to withstand high temperatures, tons of pressure. It's literally getting placed with a ton of tonnage between it, steel on steel conditions. So we need steel that's going to last a long time. As tool makers, we want steel with known characteristics. We want steel that has been utilized within injection molding, and it's proven to have that durability and accuracy that we need. In terms of specifically with 3D printing, if we're going to print something and it's not going to be faster than what we're already doing today, there really isn't a value there. So in terms of specifically with new technologies within tool making, we're looking for something to enable us to do something better or faster. And then the last thing that tool makers need is a new highly skilled piece of equipment that requires more highly skilled people on the team. And so we're not looking to make our lives harder. We're really looking to make our lives easier. So in terms of our specific journey with 3D printing, we've been exploring additive metals since 2017. This is mostly driven by the fact that we want to be a leader in innovation for our customers, but also our customers really needed us to expand here. Our customers have been looking for conformal cooling, and they've been looking for us to find ways to deliver, faster and more affordable solutions for them. So some of the things that we've been looking for, the first would be tolerances. I spoke about this in the previous slide. We're hitting tight tolerances. Anything over plus or minus 3 thou really isn't going to get us close to where we need to be. And there's a lot of post-processing that's going to be needed in order to get us there. So that was really a key point. And prior to Mantle, there really wasn't a technology we had explored that could get us under 5 thou. We're also looking for flatness and stability. I saw that there was a handful of tool makers here, or at least have tool rooms. And if you've worked with 3D metals before, then historically, the moment you go to machine them, they move all over the place. And so if I have to have my most experienced tool maker, or I have to carry a handful of spares, or I have to kind of go above and beyond in order to bring this piece of steel into spec, why wouldn't I just do it the traditional way? And that's something that we've really struggled with in the past. Another thing is materials. We have experience where the tool steels weren't familiar or proven within molding. And so not only were we hesitant to utilize them, but we really weren't confident that our customers were going to be willing to integrate them into their production molds. And lastly, cost. So I look at cost in two ways. The first is that my investment. So as a tool maker, I only have so much capital investment that I'm making within a year, and I didn't want a 3D printer machine that was going to take up years of that investment. And I also didn't want to have to price my 3D printed inserts so high that it no longer was valuable to my customer. And so this was kind of what we were looking for and the challenges that we were seeing until we met Mantle. So we met Mantle in 2019 at the AmeriMold conference, and we immediately started doing the basic tests that we were doing with all technologies that I'll show you in a moment. But they quickly were surpassing what we had experienced before, and we got very excited. Some of the things that we were seeing with them, the first is the surface finish. So they come off of the printer at a D2 or like an EDM Charmy 26. And I have a handful of inserts here that you can see, but here's some examples of what it looks like. I didn't have to touch any of the part geometry in this. So that's what the surface finish looks like coming off of the printer. And for us, that was huge. It also, you can see when you're looking at the prints, you can see the density of it. There's no voids or pitting, and that was consistent even if you sliced open a block that you had printed. Another great thing that we saw with Mantle was accuracy. We're achieving plus or minus 1/1000th per inch. And this was huge for us. In some instances, since integrating the machine, we're seeing even tighter tolerances than that. So this was, again, just a jump forward, a leap forward in being closer to that finished product after printing. We're able to achieve very fine details with Mantle. We're able to get down to a 5 thou corner radius. And so we're able to achieve some of the, sharp details that you're seeing in these images. And again, that wasn't something we had seen in the past. Flexible cooling designs. I'm actually going to talk to you about a handful of conformal cooling applications we've done. But we did put Mantle to the test, and we wanted to prove out that the surface finish and density of this was actually going to withstand some of the cooling channels that we wanted to put in. I think a very important one for all of us is the stability. It performs and acts exactly like standard tool steel. It has the same chemical properties as standard tool steel. So they have an H13 and a P20 material, which I know Ethan's going to talk a little bit more about. And lastly, the machine is extremely easy to use, and that was something that was we were very surprised to see. We kind of would say you basically need some entry-level CAD experience, some entry-level CNC experience. But Ethan's going to tell you about how the programming really does a lot of the work for you. So the software does it for you. You don't need an expert programming and understanding how to operate this. So in terms of, I think this is for most of us looking to integrate printed steels into our molds, this is really what matters. It matters that it is compatible with traditional manufacturing operations. And this was something that we spent years proving out with Mantle. We have polished it to an A2 finish. We have welded it. We have chemically etched it. We have wire EDM'd it. We have sinker EDM'd it. We've drilled, we've ground. I mean, we've done everything that you could. Yeah, this is a really great photo here that you can see just a handful of different operations being done. And what's impressive is not that you can do this. What's impressive is that I don't have to change my operations in order to achieve it. And so there's no added resource or added time in order to finish machining it. So the savings that you get from printing and sintering actually turn into and translate into value.
Awesome. Yeah, so as Hillary mentioned, Mantle's technology was able to achieve what they were looking for with metal 3D printing and what they needed for tool making. And the reason that Mantle was able to do that was because Mantle was designed specifically for printing the tools that she's making and using every day, which is what's so unique about Mantle is that we set out to print the inserts, the molds, the components that are going into molds that users are using every day, that tool shops, plastic processors, injection molders are using, which is what's so unique about Mantle's true shape technology is that we were designed specifically for printing the tools you're using every single day. So with Mantle's true shape technology, we're offering the accuracy of a CNC machine with the added benefit of a 3D printer. You're getting all those benefits that are widely known with 3D printing, from lead time and cost, of ease of use, to flexibility with design, but with that added accuracy of CNC machining. And I'll talk a little bit about how that's working in just a couple of minutes. Additionally, the system is designed and priced for every single shop. As you may see, it looks very similar to a CNC. It's designed to be on the shop floor. It's designed to sit next to your EDM equipment and your CNC machines and your grinding equipment. It will sit right at home on your shop floor, making it very, very easy to implement and very, very accessible for all shops and processors. One thing I want to say is that, Mantle didn't just set out to design a very cool 3D printer, design something that can print accurate parts or surface finish. At the end of the day, Mantle set out to make a difference to the injection molding community, to the tooling community. And Mantle technology has shown results. We're going to talk a lot more about use cases later on, but I just want to briefly talk about this relatively small insert that was used for molding a consumer product. But the accuracy here on this insert was within a thou. The surface finish was equivalent to a standard insert that they would have made with traditional processing. The parts were all standard to the traditional process as well. And after over 200,000 shots, there was no wear on this insert. But what really matters was that the company was able to produce this insert with a 70% lead time savings and a 65% cost savings. Because at the end of the day, it's great that we can print accurate parts. It's great that we can print parts with beautiful surface finish. But what really matters is how are we adding value to a manufacturer, and how are we making a difference and solving the problems that people are having today, which are often really high lead times and very high costs. Another quick poll before we get into talking about how our technology actually works and how our 3D printer works. I'm curious to hear, what is your current experience with 3D printing, and how are you using 3D printing today? Awesome. Seeing some results come in.
Yeah.
It's great. Awesome. So it looks like a lot of people doing plastic 3D printing, which is awesome for prototyping, form and fit, for jigs and fixtures. I assume awesome to see a lot of people doing plastic printing, a couple people doing metal, a couple people outsourced, and then obviously a couple people who are, right, that's why you're here today, to learn more about 3D printing in general and maybe looking to do it in the future. So to talk a little bit about how Mantle's technology works, Mantle's technology is really a solution. We call it true shape technology, and it's made up of a couple of different building blocks that you're seeing on the screen here now. When it comes to hardware, there's both a printer and a furnace. And again, as Hilary mentioned, designed to be very, very easy to use. Minimal training, very, very easy to operate. It's designed to go onto the shop floor using similar power and air requirements, etc., that it will sit right at home on your shop floor. When it comes to software, we're kind of the brains of the whole true shape operation. Very, very easy to use. It's going to automatically generate all those tool paths for you, both additive and subtractive, and we'll talk about how that works. And of course, there's no CAM programming required, so you don't have to be an expert in any CAM software. Realistically, we could train anyone on this call how to use this technology very, very easily in just a couple of hours. And then finally, our materials, our tool steels, as Hilary mentioned, H13 tool steel, a very common tool steel in the injection molding industry, and then P2X, which is very similar to a P20 material. Our tool steel, as you may see, looks a little different. It starts as a paste, and I'll talk a little bit how we go from a paste into a final steel insert that I'm showing you here right now. So within our two pieces of equipment, there's the printer and the furnace, and there's really three main steps that are happening. Within the printer, we're doing our printing and our shaping. Within the furnace, we're doing our sintering. So within this printer, we are printing and we are shaping. So we're laying down our paste, which is our metal paste, which is a combination of metal powder mixed with some solvents to allow it to flow. We're going to print a layer of that paste, and then every single layer we are going to mill perfectly flat with an end mill. We're then going to deposit more layers, and after a couple of layers that are printed, usually about 10 layers, we're going to come back and refine that shape with high-speed cutting tools again to add feature details, to remove layer lines that are very common with most 3D printing processes, to really refine the shape and really produce a very, very crisp, accurate part. So all within our printer, we are both printing, depositing our paste layer by layer. We're also milling the part as well to refine that shape and add that feature detail. So that's where we get our kind of hybrid process here inside of the printer of printing and shaping. Within the furnace, we then take our entire plate out of the printer, or the part out of the printer, and put it into the furnace. The furnace gets just below the melting point of the material, in this situation, our tool steel, and it's going to densify our part. It's going to take that metal powder, it's going to sinter it together, and the result is a dense, strong, hopefully you can hear that, but the result is a dense, strong, durable tool steel component. So three real steps here: print, shape, and sinter. But the result is you get an insert that can be used for molding directly with very minimal post-processing. Example here of a slide, a relatively big part that I have here, but this slide was able to be used without any post-processing to the feature detail here. It just did a little bit of grinding to get it into the mold base. And this was used to inject some components out of a 30% glass-filled peak. So a very abrasive, very high temperature material. It's actually kind of heavy in my hands here, but just speaks to the durability and the fact that this is the result out of the furnace. So 3 steps to get you an insert that can be used with really minimal post-processing.
Yeah, so as we've kind of alluded to, we did get a beta machine this year. And so I just want to kind of walk you through a little bit about what we've been doing with it. So we received our machine in June. And since receiving it, it's been almost running 24/7. We've been utilizing it internally. We've also been utilizing it with some OEMs directly, as well as contract manufacturers and even other tool builders. And having it just since June has really exposed us to not only new customers and new opportunities, but a whole new value stream that we really didn't have access to before. So what are the ways that we're using it? What I'm going to do now is just kind of walk you through some examples of how we've been using it at Westminster Tool. So the first way that we're utilizing it is for conformal cooling, and you can see an example here in the image on the right. So Westminster Tool has already been using Moldex 3D to drive decision-making in terms of cooling and gating to optimize our molding process and our tool designs prior to sampling. So this was kind of a natural integration. We've already been doing conformal cooling, but now we have the ability to manufacture it in-house. We have better control, and we're also able to do it much more affordably and quickly than we could in the past. We were using braze technology before. It would take about 8 weeks, 6 to 8 weeks for us to get a base, just basic geometry, and we'd have to do all of the post-machining work to it. It did move all over the place, and so we had some of those challenges, whereas now we're able to get pretty close and then go in and do any finish machining that's needed. And with this, we've seen a huge reduction in cycle times and scrap rate. I'll give you an example coming up here, but in this example on the right, this was actually an industrial cap. The inside has threads, and the customer was actually jumping the threads instead of unscrewing. So as you know, you have to wait for the perfect amount of cooling to happen, just enough for those threads to solidify and be able to jump them without damaging them. And they found that this was driving an increase of 10 to 15 seconds in their cycle time. So we explored we went up and down, around, we explored all different options in Moldex 3D on different cooling channels. This is what we went with, and we were able to reduce the cycle time by 10 seconds, which was what their goal was. Another thing that we've been doing is advanced prototyping. So as I mentioned, we do work with a lot of aerospace and defense customers where they're molding things like PEEK, Torlon, glass-filled nylons, and they need a more robust prototyping solution to be able to shoot those very high temperature plastics. And so that's another thing that we've been doing, is helping them to do kind of rapid prototyping where there really isn't finished machining in the product area that we need. And I am going to give you some examples of these as well. And then lastly is development tools. So really, once a customer has already done rapid prototyping, they've already established what the product is, and now they really need to learn on a pilot or a bridge mold exactly with as close to mirror environment as what a production mold is going to run. And traditionally, when you were doing this, you were building a full Class 101 injection mold, which could take anywhere from 6 to 10 weeks. And we've been able to drastically reduce that, utilizing either our own in-house frames or our customers, printing an insert in a week and then taking 1 to 2 weeks in order to finish it on the back end. And so it's really enabled us, and we're not sacrificing quality for them. So we recently did a project with a lot of complex shutoffs that we were able to manufacture in 3 to 4 weeks. And something like this would have historically taken us at least 6, if not 10 weeks or more. And so to be able to accomplish some of the geometries that we are with the minimal post-processing has really made a difference for us and our customers. It's also a great way to trial conformal cooling in a quick way that you're going to duplicate in a production environment. So some examples. So some of you may have seen this before. This was actually a project that we did when trialing Mantle, when we were first kind of evaluating the technology. And the key here was that we wanted to explore something that we already had internal experience molding. So this was an automotive part. It's a 43% glass-filled nylon, and we had molded for this customer about 10,000 once in a while as needed. So what we wanted to do is trial, if we were to integrate conformal cooling as we normally would, what could the impact be actually on our customers' output? So we asked our designer to put some complex lines in there, because what's the benefit of printing if you don't get complex? And so we challenged him. These are the lines that are put into it. This is actually the component here. So those lines are inside of this. And it took us 5 days to print and sinter that. And then we had another week of post machining. And you can see those lines there. So we, in this instance, were able to reduce the cycle time by 25%. It came off with a D2 EDM finish, which was perfectly fine for this case. And it also saved us at Westminster Tool 25% of our attended manufacturing hours versus traditional. The tolerances were all within 2 thou on a 3x3x2 insert. And it just really allowed us to eliminate a lot of the post-print machining that we had experienced in other cases. So we really challenged the complexity that we could accomplish with Mantle, but we also were internally measuring how much time we could actually reduce in manufacturing these. And we wanted a controlled environment where we can know we made these inserts traditionally before and what happens if we make them later. So not only did we make them faster, but they also had this advanced cooling in them. And so that was a really awesome example of what we could do. Another project that we did was what we called the tweezer project. So this was actually for a compounder who was releasing a new material. It was a bio-based, a castor bean-based, recyclable 65% glass-filled PA11. And they needed a robust prototype quickly. They came to us about a month and a half before a big trade show, and they wanted a really high quality part quickly utilizing this high performance material. And so we went from, they actually just gave us a concept. They said, hey, we want something like this. It wasn't even this actual pair of tweezers. And so from design to molding 2,500 parts for them, it took us about 3 weeks. And so you can see, you're not gonna be able to see well, but we did not touch the actual part geometry on these parts. We only touched we only had to do we squared up the block and put in ejector pin holes. I'll show you in a moment. But I did want to point out that in the bottom picture here, you can see that we also put a contoured cooling line, and we utilized an extra plug hole in the back just for easier access for cleaning that U shape if needed. So in terms of the details of what did we have to do afterwards? So now I think I've kind of started to build a case of what you can do with Mantle. After we printed it, we had about 7 days to finish machining it. We did not touch the part geometry. So the tweezer geometry itself was not touched. What we did have to do is we burned in the subgate. We hole popped our ejector pin holes. We did machine in our primary vents just based on the tolerance of those. We ground the entire perimeter of the block. We squared up the block, and then we ground the shutoff surface just to make sure we had a really good shutoff. And then in this instance, we laser engraved the company websites. So when I say I had 50% of the cavity complete, it's not the part geometry that I had to do. These were just the additional operations that you need in order to make an injection mold work. In general, with Mantle, the post-processing that we have to do is for tight tolerances. So if that 1 thou isn't sufficient, then you'd have to go in and achieve that. Tapping holes, any design constraints that we might not be able to achieve, mold fitment and surface finish. So like we've mentioned multiple times, comes off at like a Charmy EDM finish. So if you do need, a B or an A finish, then you'd have to polish that. And the last example that I wanted to show you was we were actually trying to address 2 challenges. This was working with Pepsi. There was 2 challenges that they were having with this injection mold base, or blow mold base, sorry. The first is that after a few hundred shots, they started to get heat-related blushing. And so they were getting cloudiness at the base of that bottle, which obviously isn't acceptable. And so while these were for trials, that was really difficult to be dealing with. They have to, let the part cool down first before going back to do more. And they had been molding these with a plastic material, a PEEK material. That didn't last as long as they wanted. As soon as they're done prototyping, they go into pilot, and they need to run about 10,000 or more shots. So what we were trying to do is both eliminate that heat-related blushing and give them a base that could last longer, that could go straight from prototype into that pilot development area. It took us about 8 days to print this, print and sinter. It was about 4.5 inches in diameter. And we only had a day of post-machining. We ground the top and bottom, and we hard milled the OD of the base and the O-ring. And so I tried to give you some good examples. We've done many more projects of even just printing for people and letting other tool rooms finish machining them. But so far, we've been really impressed and really grateful for the ways that we've been able to use Mantle.
Awesome. Thank you for that insight and all those awesome applications. Just have a couple more additional use cases that I would love to share with you, and then we're going to do a bunch of Q&A at the end here. The first one is from Fathom, located in McHenry, Illinois. If you're not familiar with Fathom, they're one of North America's largest on-demand digital manufacturing platforms. They're located all across the country, doing all sorts of manufacturing, from 3D printing to injection molding to machining, etc. Summit Plastic and Tooling, which is a subsidiary of Fathom, is a state-of-the-art mold making company. They do provide high-quality plastic injection mold design, mold making, as well as close tolerance actual injection molding. They have 15 presses ranging from 40 to 350 tons, and they have capabilities of doing a lot of different advanced molding techniques such as multi-shot tooling, bi-injection tooling, insert over molding, and as well as most conventional molds. The application we looked at with Fathom was this dental guide for this dental component. It was a customer that was looking to ramp up production, so was looking to get some parts made as they were looking to move into production. The part featured a lot of very intricate details that would not have been able to be machined, so would have required extensive EDM work, sync or EDM work. So Fathom identified it as an awesome part to try Mantle's technology with. With Mantle's technology, they were able to see a 40% reduction in lead time. That went from 200 hours down to 110 hours with Mantle's technology. Most of this savings came from reduction in EDM, as I mentioned, because they didn't have to do anywhere near as much EDM work because they were simply able to print the features into the part. I should have held up the parts for you to see here, which is the tool has right here. Additionally, there was no finishing done to the parting line. All they had to do was they still had to do a little bit of EDM work to touch up some of these features, as you're seeing in here, and they did a little bit of polishing to the insert as well, just to ensure they got that really nice surface finish on the final molded part. So a great example of Mantle technology where they're able to eliminate a lot of EDM work, which resulted in a 40% reduction in lead time. And just comparing how they would have made these parts with conventional toolmaking with Mantle's tech versus with Mantle's technology, you can see they're able to remove, of course, that programming, that rough milling. They still had to do some heat treatments as they heat treated the part after printing. They had to do a little bit of fixturing, much less EDM work, and then a little bit of final finishing. So you can see how they're able to go from 200 hours down to 110 hours, which is just a great example of an application where even though they still had to do some traditional post-processing and some finishing to the part, they still saw a huge reduction in lead time. Another great use case is Nicolay Plastics. They have a couple of different locations located in Wisconsin. They are an injection molder that is specialized in molding of complex parts in really all sorts of different volumes, from low, medium to high. They have over 40 presses ranging from 30 to 610 tons. They have a tool room that can provide them both in-house maintenance as well as end-use tooling for their customers. They work across a wide variety of different industries, everything from food service to packaging, medical and dental applications, consumer, agriculture, and even industrial. The application that I want to share with you from Nicolay was this mold, or the core. There's actually three pieces: a core, cavity, and an insert that goes inside of this slot here. This was used for molding a cam lock latch, which is used to hold a PC or a tablet in an emergency vehicle. If you know, when you see a police car and you see they have their computer up on their dashboard, which never seems overly safe to me that they're on the computer while driving, but they have this device that's used to hold that computer in place on their dashboard. The actual part was relatively complex, as you can see from all these different angled faces in here. So again, would have required extensive EDM work to produce this part. In addition, the actual plastic part was being produced in a nylon 6/6 that was 35% glass filled, so a relatively abrasive material that required a tool steel insert. So using Mantle's technology, they were able to go from a 6-week lead time down to just 2 weeks. In terms of operation time, it went from 150 hours of operations just down to 11 and a half hours. All they had to do after printing was complete was dust up the parting line, grind the outside, and add the ejector pin locations so they could get it into the mold frame. So really a massive reduction here of 6 weeks down to 2 weeks, and most of that coming from the ability to remove all the EDM work that was required. Again, looking at how they were able to reduce that tool making, really cutting out almost all the operations that would be used for traditional tool making processes to produce the part with Mantle, to go from 6 weeks down to just 2 weeks. Just a great example of Mantle. I really like this part. Hopefully you can see that okay on your screen. Lastly, want to share an example from Tessie Plastics. Again, they're located in a lot of different locations around the world, actually. Founded in 1973, they've grown to become a very, very large-scale global contract manufacturer with almost 2 million square feet of facilities. They have a wide variety of different capabilities, everything from product design to rapid prototyping, tool design and build, automation, assembly, and of course, plastic injection molding. The part I want to share with you today was Tessie has a tool that has 32 cavities that's used to mold 6,500 of these deodorant stick thumb wheels, which I'm sure looks pretty familiar to many of you used to advance your deodorant stick up through the tube. 6,500 of these per day in a polypropylene. What Tessie wanted to do was to evaluate the durability of Mantle's material through a study. So what they did was they took 3 of the inserts out of the tool, 3 of the 32. They printed 1 in Mantle's H13 tool steel, 1 in Mantle's P2X tool steel, and they had 1 freshly machined out of S7. The tool has been running since February of 2021 and has experienced over 1.4 million cycles and counting. That could be closer to 1.5 million cycles because it's running as we speak, and they've seen no signs of wear on this printed tool, which is especially significant since this has a lot of shutoffs on it, which is actually being shut off with S7, and they have seen no signs of galling, wear, or any flash on the parts. So this was just a great example of showing how just the durability, speaking to the durability of Mantle's tools, and that they are true production tools. And while it's great for prototyping, you can go to production with a Mantle tool. And again, they also were able to produce this. This was about a 54-hour print, 6 hours of post-processing, compared to it took them 150 hours to produce the insert via traditional machining. That's all we have for you today. Briefly, we'd love to just wrap up and ask, what would you like to see more of in the future? We're, of course, going to do questions and answers, and we're happy to answer. We see some questions coming in already, but we'd love to know in the future, what would you like to see more of? We're going to do lots more webinars, produce a lot more content. So what would you like to see more of in the future? This a little bit more time.
Oh, there. Comparison.
Yeah.
Yeah.
Not surprising seeing a lot of people. When I was writing this response, I was like, they're going to like this one, which is definitely something we're always looking to do, to make sure to comparisons to traditional and to help educate as well as when does it make sense to use Mantle? When does it make sense to use a traditional process? Yep. It's something that I think, we can do a good job of educating the industry on. This is super helpful for us to see, just to help, what we'll be doing for the next webinar. Just quickly jump to here, but at this point, we're happy to take any questions you have.
Excellent. Well, thank you, Ethan and Hillary. We already have a bunch of questions in, so we'll just dive right in. Regarding, we have a couple around the size. I guess the first was for the prototypes you're mentioning, what's the size of the plastic part, but then also what's the maximum mold size, core and cavity. So I guess maybe if you want to talk about, kind of target applications in terms of what Mantle can print.
So to show the size of some of the plastic parts we were talking about, you can see, for example, this is an insert to do a threaded insert. So, a relatively small part, probably a few inches in size. Relatively, this is a relatively large part. This is 7 inches long. I think it's 3 inches tall. So this would be a large part for us. Currently, the largest part we are building is a 6 by 6 by 4 inch part and smaller. But we really see the most added benefit in part sizes that are in the 4 to 5 inch range. Things like this, parts like this, just because one, print time, how long they take, as well as just have, the quality of it. This is really an ideal part size for us. I don't know, Hillary, if you can speak to what you've seen. So far, I know you have some bigger parts here.
Yeah, I think majority of what we're doing, just to kind of give you an understanding, is in this size range, which is about 2 to 3 by maybe 3 to 5. This is pretty consistent with the size tools that we build even before Mantle. And just so you know, you can print within the printer. On our beta, we have a 6 by 6. But the production units will have 8 by 8, which means that for me, I can print the top and bottom cavity of this at the same time. And that time is driven by the height. So I can accomplish this in the same amount of time. So all of these, both the tweezers that I showed you, as well as the other tool, it was about a week to print. That's an average of what it's taking us at the present moment.
Yeah. And one thing that's great to know about, that you can utilize that full build volume. So on Friday afternoon, when you're going home for the weekend, you put a bunch of parts on the build, come in Monday morning, and you have a couple inserts all ready to go into the furnace, which is awesome just to think about the hands-off nature of it's working while you're sitting on the beach and enjoying your weekend.
There you go. Excellent. I had a question here, and I know you touched on with the Tessie case study that you're achieving quite a few shots, but maybe wondering about the average shot life for the tooling, or I guess if you have some production tools out there that you can talk about, and then say the shot life has been reached? Can the insert be? Would you have to remake the insert, or can you do repairs like you would with a typical insert?
That's a great question. So I am not aware of any tools that we have printed that have failed or have reached a shot life so far. Technology is still pretty new. So as for example, this is definitely our highest volume application that I can speak to today, which is around 1.4 million shots for the polypropylene. But one thing to know is that 100% these tools can be repaired with traditional welding operations, laser welding, or just standard welding operations to build the part back up, which is very important. We knew that was going to be important for our technology. So we ensured that, again, all of our technology, our parts are fully compatible with traditional finishing operations, machining, grinding, EDM, plating, even welding, etc. So you can absolutely repair these tools. And we actually have done some studies on that I can share with you afterwards.
Okay. Yeah. And I did see the question. There was a question regarding nickel plating, and that has been done. Mantle themselves have a handful of cases, and we're in the process of doing that with a customer now. As well as exploring plating cooling channels as well. So there are some things that we've done, and we had to weld one of our tools, just learning things throughout printing, and it molded no problem. It repaired perfectly, and so we personally have run 25,000 shots. That's what we've gotten up to, but I know that a lot of Mantle's customers like Tessie, have gotten way beyond that.
Okay. And within the same question, they were also wondering about, could it be used for side action tooling? I think one of the applications you showed.
Yep, absolutely. It can certainly use this for not just corn cavity inserts, for slides, for lifter heads, etc. This is an example of a slide that was coming into the side to mold this component. So it can certainly be used for actions and etc. And really a wide variety of mold precision components that need to be made out of tool steel.
Okay. This individual was wondering about how you're compensating for the shrinkage during sintering, or if you want to talk a little bit about how.
One thing that's a bit unique about Mantle is we start as a paste. We do sintering, so there is some shrinkage in the furnace, but our shrinkage is less than 9%. Which, if you're familiar with other sinter-based additive methods, you usually see 18 or 19%. If you're familiar with metal injection molding or press and sinter technologies, same 18, 19, 20% are pretty common. So we are able to achieve less than 9%, which is really allows us to control a very uniform shrink and hold these tight tolerances. So our software is going to fully account for that shrinkage for you. All you have to do is input your end use part. This is what I want to get out of the furnace. We're going to automatically scale that part for you, and that's what's going to be printed. Because, and really a lot of that, the ability to have such low shrink comes from our paste material. It's highly loaded. It's a very optimized material, which allows us to get a very, very tight green body, which allows us to have very, very minimal shrink, which is really critical for our process and critical for creating precision parts, which when you're shrinking 18, 19%, it's much more difficult to control those tolerances.
Yeah. And one thing I did want to add is that that's built into their program. So you don't have to design that shrink into your part. When you upload your CAD, the software is automatically going to apply that shrink since it's so consistent. It is able to just apply that internally within the software, and out comes your part within the spec that you needed it to be. So it's not an added step. That was the fear we had, was that we were going to have to train our designers to design with an added shrink and all of that. So, and it's very consistent for us. We very consistently know exactly what we're going to get off of that printer.
Okay, gotcha. Excellent. Individual here was wondering about the hardness of the steel types. It looked like you had two steels you can use if you can get into.
So the H13 comes out of our furnace at a 46 HRC, and then can be heat treated. We've heat treated easily up to a 52. The P20, I believe, is around a 28 HRC, correct?
I think, and it can go up to 30.
It can go up into the mid 30s. Can follow up with you afterwards with our spec sheets. We have full material data sheets with all the properties available, but for our customers using H13 are usually pretty happy with the 46 that you can get, and if they need to go into the 50s, they can.
Yep.
Gotcha. Okay. And that kind of touches on, we had a question here about the materials that are available. It sounds like you have those. Is Mantle pursuing any other materials that you can speak to, or what?
Today we have an H13 NRP2X, a P20 material. I'm not going to speak necessarily to what's next, but certainly are going to be continuing to develop common molding materials. And that's very much driven by our customer base. When we're getting asked for, oh, I wish you had, this or that. Certainly we are in process of developing more materials, and we'll have more tooling materials released in the near future.
Okay, excellent. And I think Hillary touched on this a little bit, but the individual was wondering about what software is involved, and do I need someone to program this machine?
Yeah. So I know we've touched on it a couple points, mostly briefly though, but super important to know is that the software is very much designed to make this system very easy to use. So really all you need to do is upload your CAD file. It's going to automatically scale that for you. You can add a couple parts to the build if you would like to. You have a couple basic parameters to select if you want to alter, the machining profile or the deposition profiles, etc. But then it's going to automatically generate all those tool paths for you, and then you just upload it on the printer and you're good to go. So you don't have to do any CAM programming. It's a really, really quick process. When I was onboarded at Mantle, I think I learned how to do it in an hour.
Yeah.
So, I'm pretty confident that we could train anyone on this call in an hour how to start our Mantle machine, which is pretty impressive to think that with a couple hours of training, you're able to produce something this complex, which is pretty incredible.
Most definitely, yeah. What is the surface finish of the printed parts?
Yeah, so again, it's a 1 to 3 micron RA, which again may not mean anything to you, but it's about a D2 or a EDM-like finish. So if you see your parts,
26.
Charmy 26, so kind of what you would get off your Sync or EDM process. I don't know how well these are coming across on the screen here, but certainly no layer lines or anything like this with this process. And we see a lot of customers using not having to touch part detail because it's sufficient because it is Sync or EDM quality. So they're able to save a lot of time and cost by doing that.
Gotcha. Okay. And then
great questions.
Yeah, great questions.
Yeah. No, definitely. More of a general one. Just how long does it take to print a part? I don't know if there's.
Yeah, sure. So,
let me show this one.
Sure. Yeah. So like this is the testing this part here. This is the core. This would be a 54-hour print. So 2.5 days roughly. Very, very part dependent, right? Size dependent, complexity dependent. I don't know. A couple other examples here.
Yeah. So when I printed
parts,
these two, if I were to print the top and bottom cavity of this together, it takes a majority of the build plate, and this took 7-8 days to print and sinter. But if you had smaller things, your cost and timing derivatives really multiply when you do multiple things. So for example, if you want to hold up 2 more smaller things, you could load up a block with a handful of different things. You could do some slides, you could do 2 molds with a top and bottom cavity, and then you would be splitting that amongst 3-4 projects, both the cost and time savings.
Yeah, and it's I don't know. It always seems to blow my mind to think that to make all 4 of those parts at once on the printer, maybe over a weekend or 4 days.
Yeah,
to think about how much time and how much user interaction it would take to build that with traditional methods is a very, very stark contrast.
Yeah, definitely. Just kind of maximizing the use of that 8-inch build area, I guess.
Absolutely.
Question here on, so there's a time savings, but how does material cost compare to traditional, and wondering about a service and warranty?
Yeah, so in terms of costing, it very, very application dependent, right? If it's something that you can machine easily, that doesn't require a lot of EDM work, you're probably better off machining it in EDM. That's why every shop, they didn't replace all their machines with Mantle machines. It's a complement to the technology. So for, like I mentioned a few times here, where we see we're adding the most value is really when we can reduce EDM and hard milling steps, which is really, so parts that are relatively complex, have thin ribs, have a lot of different, angled faces, etc. Organic geometries are really, really great for us because that's where we can see big reductions in EDM steps. And happy to talk after this and share more costing information on some of the parts, or look at your parts even to let you know what they would have cost with our technology. And same goes for warranty and things like that.
And in terms of Westminster Tool, how we're handling the warranty of the tools that we're building, right now it's very dependent on your geometry. So if you have something like the parts I've been showing you with a lot, I think that part 64 steel shutoffs. If we're rushing to push that through, that's a quick development type tool. We're not putting Class 101 design standards built into it. Then we're going to warranty it for what we're building it for. But at the end of the day, it's H13. So if I were to put that component into a class 101 tool, that's the rest of the tool is guaranteed for 1 million cycles, then I am designing that component for 1 million cycles, and therefore we're standing by it for that. So we're not really approaching it any differently than we would do with any other steel component. Hopefully that answered your question on that part.
No, I think so. Regarding the conformal cooling, do you have to have any support material involved when you're printing the conformal cooling channels?
Yeah, so it depends on the size of the channel. Today we print a lot of our conformal cooling channels with a teardrop shape, just so that way they self-support, which we haven't really seen any issues in the actual effect of the channel. It performs the same. If anything, it actually increases the area of the channel, which can be beneficial for molding. And then afterwards, as Hillary mentioned, you're going to come through and tap and add your lines anyways. So you can just, you're going to drill into it. Essentially, it's a pilot hole at that point. So generally, we don't need any support materials for conformal cooling because we're using those teardrop shapes.
Gotcha. Okay. How much attendance does a printing process need? You mentioned running several parts over a weekend. Is a printing, drying, CNC process set and forget? This individual was just kind of wondering about how lights out it can be, compared to maybe, I guess, like an FDM printer.
I'll let Hillary answer that.
Yeah.
They have the machine and they're using.
Yeah, honestly, I would say in a standard 1 week print, you've got about anywhere from 2 to 4 or 5 hours tops of attended time, and that's running 24/7 for 8 days. You do have to manufacture your base plate, which is a whole detailed step, but it's very simple. So there's that. There's the setting it up, just kind of making sure that everything is ready to go in the printer, making sure the paste is loaded into the feeding channels, and then on occasion eliminating the waste. So, and moving it over from the plate into the furnace. And so it's hours in comparison to how much it's running. So very low unattended, which has been a great way to add a resource to our shop without adding a person.
Yeah, absolutely.
Gotcha. No, definitely. Excellent. Well, looks like we have a few more questions coming through. Let's see here. All right. Well, I think we've gotten through most of the questions here.
Any questions? We'll certainly follow up via email.
Yeah.
But I just want to encourage, thank you everyone so much for giving us an hour out of your day today. It means a lot to both of us. Feel free to reach out to either of us. We'd be more than happy to chat more in detail about our technology, answer any more questions. And I'd love to hear more about your applications. I always learn a lot from calls like that to hear about how you're building tools today, how you're thinking about manufacturing, and to help you understand it if Mantle could potentially add value to what you're doing today. So please don't hesitate to shoot me an email or shoot me a call. Always happy to chat.
Yeah.
Excellent. Yeah. Well, thank you, Ethan and Hillary, for an excellent presentation, and thank you to Mantle for making this possible. Want to thank, as Ethan mentioned, all our attendees for spending some time with us. I think you definitely learned some things. I know I did. A lot of great questions. Want to remind our attendees that everyone who registered for this webinar, you'll be emailed a link to a recording of it. So if you want to rewatch it or check in on some other things, and then also know that the webinar recording will also be posted to the Plastics Technology website. So you can check it out there later and watch it on demand. So once again, thanks to Ethan and Hillary for a great presentation, and thanks to Mantle for making this possible. And I hope everybody has a great day. Thank you for joining us.
Thanks, everyone.
Bye.